This is our opening lesson on antiderivatives and indefinite integrals. We will go through many examples together so that you may start to build your understanding here of antidifferentiation. Once we have gone through about 10 examples together, the expectation is that you will be able to do the problems in your lab manual, pages 59 and 60. Before we jump right in, let's really just kind of get an understanding of what is meant when we say antiderivative. Really, we're going to be looking at the reverse operation of finding a derivative. And basically, what's going to happen is we're going to be given a derivative and asked to find the function. So I want us to start off just by looking at the antiderivative in a very simple sense and develop the theorem that we will use here to begin with. So if you would, let's take a look first at the antiderivative of the function f of x is equal to 5. And what I want you to think about here is there are actually several functions that have a derivative of 5. Those functions might be things like 5x, 5x plus 1, 5x minus 3. I'm sure you could think of many, many more. The second example, suppose I asked you to find the antiderivative of the function x squared. So here we're looking for several functions that have the derivative of x squared. So our thinking becomes a little bit more complex now. But in general, and you will learn how to do this in a minute, we would have the function 1/3 x cubed would have a derivative of x squared. Again, think of our function 1/3 x cubed. And if we moved through our derivative rule for polynomials, we know that we would bring down our exponent, multiply it by our coefficient, and reduce the power on our exponent by 1, leaving us with a derivative of x squared. We're going to learn how to go backwards in just a minute, but I want you from this slide to be able to pick up that what is differing at most is a constant. If you look at the first one, where we had our function of 5, meaning we had the derivative of a function was 5, we could have had a number of different functions that could have given us a derivative of 5, and the only thing that would have been different between those functions is the constant at the end. The same thing with the second one, 1/3 x cubed plus pi perhaps, or 1/3 x cubed minus e. So take a look at these, study this for just a second or two, and then we'll go on and actually look at how we work with this. In this slide, it's going to be important that you understand the symbols of what we're using to antidifferentiate. So basically, we're going to be looking at the family of all functions that are antiderivatives of a function f of x is called the indefinite integral and has a very specific symbol. We read this as the integral of f of x dx. The symbol, which is, it looks like a great big S, is actually called our integral sign, and the function that sits to the right of the integral sign is called the integrand. The symbol dx indicates that antidifferentiation is performed with respect to the variable x, meaning this integral sign together with dx basically gives you directions on what to do. The directions are antidifferentiate with respect to the variable of the function. In this case, it would be x. The theorem that we just looked at said, well, if you antidifferentiate you can come up with the original function, but you would also have to add a c onto the end of it, which we call the constant of integration. Don't get too hung up in the semantics here. What I want you to understand is that you're going to be given directions by the integral sign and the symbol dx that says antidifferentiate. You will always be contemplating that c, constant of integration, and it will always be added on to the end of your function. Okay, so I want you to think about this for a second, and I will pause so that you can have the opportunity to think before I write. But suppose I make this statement. The derivative of a function is 5x to the fourth. Can you write 3 possible functions that may have this derivative? So I'm going to pause here for about 15 seconds and let you think about this. Okay, so I know the thinking for this part before we learn any rules is a bit backwards, say, but hopefully you contemplated this a little bit and you came up with, well, x to the fifth, Miss M, would give me 5x to the fourth if I took the derivative. So my original function would be x to the fifth, because again, if I had my original function x to the fifth and I took the derivative, I would end up with 5x to the fourth. Well, the problem is that is absolutely true, but there are many, many functions that we might differentiate and get 5x to the fourth, but all of those things are going to have some constant at the end, so I just did 3 possible. Yours may not look anything like mine, but perhaps I had x to the fifth plus 6, x to the fifth minus 10.5, x to the fifth plus pi. Those would be 3 possible functions that may have 5x to the fourth as a derivative. Okay, so what we're going to do here, folks, is we are actually going to look at the 5 formulas, properties, and move through these quickly. I'll give you an example of each of them, but then we will start the 10 examples that you will actually do with me that will lead you into the problems that you're going to do in your lab manual. So let's look at number 1. In our very first one, it basically says if we're going to take the integral of x raised to any power dx, the rule basically says take the power, increase it by 1, and then divide by whatever you have increased it by, and add c to the end of it. So how about I have this for my first example. The integral of x cubed dx. Okay, so the integral sign along with the dx basically says antidifferentiate x cubed, meaning give me a function that has x cubed as the derivative. Well, using the power rule in number 1, I would increase the exponent 3 to 4. I add 1 to it, and then I simply divide by the value that I've just raised it to, and I add c on. Now we're going to do lots more examples, but I wanted to give you one just to see how it works in the beginning. The next rule, the integral of e to the x dx, is simply e to the x plus c. Now, it has to be, just like when we used this with the derivatives, we can only be looking at e to the x dx, or possibly something like the integral of 3e to the x, where we have that coefficient in the front of it. We'll do some of those in just a moment. In the third one, again, this should look a lot like ln. Remember, when we were taking the derivative of ln x, the derivative was simply 1 over x. Well, now we're going to be given 1 over x. We're going to go back to ln x, but if you notice, I do have absolute value symbol around my x now. That is simply because I cannot take the logarithm of a negative number. So that just basically ensures that whatever my variable expression is there, that it's going to be positive. Again, no concerns. We're going to go through a lot of these. Number 4 is a rule that we actually use quite a bit. It's a constant rule. We use it to do all types of work with our constant or coefficient. Actually, these are going to be, has to be a factor, and that's the word that's going to make this thing different. So let's take a look at something that would involve the use of 4. If I have the integral of 7e to the x dx, again, my integral sign and my dx tell me that I'm going to anti-differentiate. It is always easy if you can look at the 7, understand that it's being multiplied by e to the x, therefore it's a factor. I can rewrite this thing as 7 times the integral of e to the x dx, and then easily anti-differentiate that to 7e to the x plus c. The last one here of our basic properties that we're going to look at basically just says if you've got any of the things in the first 4 added together or joined by addition or subtraction, that you basically can break it up into 2 separate integrals if that makes it a little bit simpler for you. So over here to the side, let's take a look at another one that would be an idea of what we're looking at there. Suppose I have something like the integral of 3x to the 4th plus 1 over x dx. Basically what that means is I have the integral of 3x to the 4th dx plus I have the integral of 1 over x dx. And using that idea number 5, I've just broken it apart into 2 simple statements, and I can take easily the antiderivative of each. As far as the plus c goes, I don't have to worry about adding my plus c until the end. So if I wanted to now take a look at working just the first one, number 5, simply going through and looking at this, I basically would have take my 4, raise it to 5, and then divide by 5. So this is going to become 3/5 x to the 5th. I'll hold on to my c until the end, plus the integral of 1 over x dx is ln absolute value of x. Now I can put my plus c on. Don't get discouraged if you're at a place where you're not understanding this yet. We're going to go through enough examples where this will catch on. This is a whole another idea of something that takes practice. When we first started the derivatives, it took a lot of practice. This is also going to take practice. Okay. So we're going to go through some examples here, and as we go through these examples, these will be the ones that I want you to take notes on so that when you go to do the ones in the lab manual, you'll be set. You'll be ready to look back and see how we approach some of these. The first one is a very simple one, the integral of 2 dx. But I'm going to take you through a route on this one just so that you'll have an understanding of how you can do every one of these where you basically just have that integral of a factor dx. So hopefully after we've gone through just one, you'll have an idea of how you would approach these. So the integral of 2 dx, the very first thing that I'm going to do to show you this is I'm going to rewrite it as 2x to the 0 dx. And the reason that I'm doing that in this first example is I want you to understand that we're differentiating with respect to x. Some of you don't see an x there, so by placing x to the 0 there, it will make your work fall into line with the rules as they stand. X to the 0, you know, is the same thing as 1. 2x to the 0 means exactly the same thing as 2. But for our anti-differentiation purposes, it makes our life a little bit easier because we can go, oh, well, x to the 0 raised or increased by 1 would be x to the first divided by 1. My coefficient or factor of 2 is still there, plus c. So simplifying certainly is just going to be 2x plus c. But I want you to think about this and really the implications of a lot of different things. If that 2 had been any factor, if it had been the integral of 5 dx, that would be 5x plus c. If it had been the integral of negative 10 dx, that would be negative 10x plus c. But we got that by thinking about this to begin with, that x to the 0 factor. Okay, let's move on. And the second one that we're going to look at is going to use the idea of e to the t. So let's see how this one works out. So some of you may look at this and immediately say, well, let's just go ahead and say 16 times the integral of e to the t dt. So that's basically saying integrate with respect to the variable t, or anti-differentiate with respect to the variable t. My factor of 16 has already been pulled out. This thing is just a rule. The integral of e to the t dt is e to the t plus c. 16 taken out, remember, as a factor. So this would become 16 e to the t plus c. All right, number 3. So this will be one where we're going to use our power rule, and you know, some people will do this a little bit differently. Some of you may look at it and immediately bring that coefficient of 3 outside. Sometimes it matters, sometimes it doesn't. I would say in this one doesn't really matter. Even the one we did in number 2 didn't really matter. You'll see some in a few minutes that will matter if you pull that factor out first. But if I'm looking at this, the very first thing that I want to do is increase my power of 4 to 5. My coefficient is 3, but I'm going to divide by 5 plus c. Now I'm going to pause here for a second. I want you to think about this. In the fractions, some of you were getting very confused. 3/5 x to the 5th means exactly the same thing as 3x to the 5th over 5. Those two things have the same meaning. It just really is depending upon your comfort level and how you like to write it. Both of those involve the rule being used exactly the same way. Okay, so in number 4, we're looking at the integral of 2x to the 5th minus 3x squared plus 1 dx. And I've already rewritten this one for you because I do want you to use the idea that we can pull this polynomial apart and make it into 3 pieces, and it will be easier really, especially as we get into some of our harder examples, for you to understand this property because it can benefit us. So if we use it for this easy example, you'll be able to transfer this to some of the more difficult ones. So you can see each of my pieces here. And what we're going to do now is just go ahead, go through, anti-differentiate, and as we do that, we know that we'll be thinking about the constant, but we can tack on our constant way down here at the end. All right, so in the first one, 2x to the 5th dx, that's going to become x to the 6th. My 2 is in front. I'm going to divide by 6. And some of you might be saying, well, you can reduce that. So if you're at that point where you'd like to reduce it and say x to the 6th over 3, that's perfect. When I move on to the next piece, I'm going to have my first pass will be 3x cubed divided by 3. Again, I increase the 2 by 1 to get 3. My 3 that you see in front, this coefficient was there, divide by 3, but some of you are at the point where you would reduce that and go, oh, well that's just x to the 3rd power. And then as I move to my last piece, maybe you're thinking already that you know what that is, and that's wonderful. Some of you may be thinking about it as 1x to the 0 power dx, like I did in the first example. But what we decided was whenever we have that factor, we could simply say, oh, it's the coefficient times x. So here, 1x is just going to be x. So if you simplify, and I would say that simplifying in this case down to this final line I have here at the bottom, I would say that that is a reasonable expectation. Some of those simple fractions you should certainly be able to simplify. But what I want you to think about here more than anything is if you took the derivative of each of these pieces, you should end up with each of these pieces. And this would be a good time to pause the video to check to make sure that you understand how the derivative and the antiderivative are related. Okay, let's look at this next one. You might think that the best way to do it is to split it up into two integrals, and that's certainly a good way to do that. So we can go ahead and rewrite this as the integral of 5 over x dx minus the integral of 4e to the x dx. So there's a couple things that you might want to do with this. Everyone perhaps may see that this 5 is a factor in the first integral and this 4 is a factor in the second integral. So perhaps you might want to rewrite again and say 5 times the integral of 1 over x dx minus 4 times the integral of e to the x dx. And then I think you might see the rules come right out at this point. We know that this 1 over x here is going to be the natural log of the absolute value of x according to our rule. So 5 ln absolute value of x minus, well here we know that our e to the x, the antiderivative is simply e to the x, so here we would have 4e to the x, and now we'll put our c on at the end. I want to start this one by you examining my original integral here and noticing how I rewrote it. Okay, so you can see the two pieces, and you'll certainly recognize that x to the 4th on the denominator became x to the negative 4 in the rewrite. So as I go to integrate this one, this is just going to be a fraction or arithmetic problem, but for some of you it's going to be a little bit tricky. So I want you to think about how you're going to work with fractions here. So if we just look at the first one to begin with, the integral of 2x to the 2/3 dx. You can move the 2 out front, there's no problem with that. either way that you do it, you're going to have to deal with fractions. So I just want to go ahead and let's get started and see what happens. So if we take x, first of all, we're going to raise it to the 2/3 plus 1 power. Okay? 2/3 plus 1, 1 is 3/3, so 2/3 plus 3/3 is 5/3. So we are raising x to the 5/3 power, and then we're going to divide by 5/3, and we've still got our coefficient of 2 out in front. We'll get to what we need to do to simplify that in a second, because that's a little bit too messy, and we will work with just making that appear in a simpler form. When we move to the next piece, our x to the -4 plus 1 becomes the -3rd power. Then we're going to divide by -3, and we still have our 3 coefficient out in front. Again, if we had put that in front of the integral sign, we would still end up with the same result here shortly. And then we're going to put our plus c at the end. Okay, this is the place where I want you to pay close attention to what's going to happen with the simplifying. So as I go through and simplify this sum, I hope that you remember that what happens here is I know that x to the 5/3 power is my variable and its exponent. When you divide by 5/3, I'm hoping that you remember that that means exactly the same thing as multiplying by the reciprocal, or multiplying by 3/5. If you don't remember your fraction stuff, go back in the beginning of the calculus book or online. You can get some good calculus, not calculus, but arithmetic review for this. So out in front now, I have this 2 times 3/5 times x to the 5/3 minus, well, over here I have a -3 divided by a -3, so perhaps I'll put plus. These reduce, x to the -3rd plus c, and I would in fact take this one step further, and I would write this as 6/5 x to the 5/3 power plus x to the -3rd plus c. So this really no different than any of the others involving our rules, except that the fractions may be something that you're really going to have to look at and understand and work with a little bit more. Okay, so this is one where we would definitely want to rewrite first. So what you would want to remember here is, what do these numbers mean? How do they relate to a fractional exponent? So the number in the radical, that exponent is going to be the numerator, and this number is going to be the denominator. When we rewrite, we would have the integral of 4w to the 3/5 power dw. And again, we're basically going to anti-differentiate here with respect to w. Some of you may in fact bring the 4 out. Again, that's just going to be a matter of preference in some of the examples. In some of the examples it's probably going to be very necessary. This one it's just going to be a preference example. So here, all I'm looking at now is, once I've rewritten it, I know that I'm going to have to take w and raise it to the 3/5 plus 1 power, which is going to be 3/5 plus 5/5, which would be 8/5. Well, when I raise it to the 8/5 power, I have to divide by 8/5. The 4 out in front of the integral remains multiplied. So that's the first pass through it. and then we're going to clean it up some. So again, dividing by 8/5 means the same thing as multiplying by 5/8. So I'm going to take that out of the denominator. That complex fraction is not preferable when writing our antiderivative here. We will add on our plus c at the end. But here, our very first pass at simplifying looks like that. And then we would go one step further and rewrite this as the 4 and the 8 will reduce 5 halves w to the 8/5 power plus c. Okay, this one, it's going to be very important that you understand the rewrite and how I got there, because in these simpler examples we absolutely want to try division before we make them more complicated than they need to be. So all I've done to go from the original integral to the rewrite is I've literally taken x to the 4th over x squared minus 8x cubed over x squared, and I've reduced both of those fractions. So I want you to look at that for a second. That is going to be a really big one for you to understand so that you don't complicate this more than it needs to be in these first examples. So I split that up into two fractions. I reduced it. Now I'm going to go ahead and just anti-differentiate. X squared plus, x squared is what we're going to start with. So that would be x to the 2 plus 1 power, which is x cubed divided by 3, minus, this is going to be 8x to the 1 plus 1 power, which is 2, divided by 2, plus c. And I can end this nicely just by rewriting a little bit so it becomes a little bit more clean. X cubed over 3 minus 4x squared plus c. And again, just reducing here to get my 4. Okay, here's another one that requires a rewrite. So as I rewrite this, I'm just going to say the integral of 8x to the 1/3 power minus 6x to the negative 1/2 power dx. Now, you can split this up into your two separate integrals if you like. I think we're at the point where you might be able to recognize this is two separate integrals, and that's how we would approach this problem. So in the first part, we're going to take our x to the 1/3 power, add 1, so 1/3 plus 1 in the form of 3/3 would be 4/3. Our 8 is still in front, and we're going to divide by 4/3, and that's quite a mess to begin with, but we'll clean that up in a minute. Then we move to the next piece, and I'm going to go ahead and start with my x. Negative 1/2 plus 1 is going to be positive 1/2. I'm going to divide by positive 1/2. I still have this negative 6 out in front, plus c. And then it's just a matter of cleaning it up. So in the first pass of the cleanup, we're literally just going to take and say 8 times 3/4. Remember, dividing by 4/3 is the same as multiplying by the reciprocal. X to the 4/3 power. Some of you might already be seeing some sort of shortcut there. Minus, well, here we're going to take 6, multiply it by 2, because when we divide by 1/2, that's the same thing as multiplying by 2. I'm going to write it like this so that those of you who don't see it might be able to see it in that respect. X to the 1/2 power plus C. And then as I continue this, just a little bit of rewrite here, make it a little bit simpler to look at. And again, 4 and 8 will reduce. So 2 times 3 would give me 6x to the 4/3 power. Here, minus 12, 6 times 2 is 12, x to the 1/2 power plus c. So again, just the idea of working with those fractions and making sure that you understand what's happening there. Okay, in this last example that we're going to do together, we see two binomials, and for right now, we have no way to approach this except to think about multiplying the two binomials together. However you go about this process, whether you use FOIL or whether you use box, there's lots of ways to simplify. But basically, when we simplify this integral, it's going to look like the integral of x cubed plus 3x squared minus 2x minus 6 dx. And then I think you can see that it's a fairly simple process from here. So I'm going to pause for a second, let you go ahead and try and work it out, and then I'll write the answer. Okay, so let's see how you did. Just simply going through this, we could split it up into 4 different integrals if we wanted, but quite simply, this is going to become x to the 4th over 4 plus x cubed, because you may remember that here we would raise our 2 to 3 and then divide by 3, giving us just x cubed, minus x squared, same idea. Here we have a 1, we would raise it to a 2, divide by 2, and then at the end, minus 6x plus c. All right, I hope these examples have gotten you started thinking about how to go from the derivative back to the original function. I believe that you have enough information so that you could really go through and try pages 59 and 60 in your lab manual. Those are going to present you with some challenges, but I think if you understand the video and use the video, come back, rewatch some of it so that you'll get a little bit more practice. There are all kinds of other videos and materials out there. I've tried to put a few more things in our folder in Blackboard. But good luck, and we'll talk about this in class.